Hey there guys, Mr. Carlson here. Let's talk about how we calculate K using our equilibrium expression. So we have this reaction right here. The question says the following equilibrium concentrations were observed for the reaction shown above, and then they list out what the concentrations were. So for a question like this where you have to calculate K and you're given the equilibrium concentrations, it's just as simple as plugging it into your equilibrium expression. So we learned this before, how to write that equilibrium expression. All we have to do is put the products over the reactants. So in this case, I have one product here, it's NH3. So we would write it as concentration of NH3 squared. Remember, we use the coefficient there to see what power to raise it to. And then on the bottom, we're going to have our reactants. So concentration of N2 to the first power times the concentration of H2, and that's going to be cubed. There's my equilibrium expression. Now I can plug in my concentrations and just crunch the numbers, and then that will give me the K value. So for NH3 on top there, we're going to have 3.1 times 10 to the negative 2. That's going to be squared. On the bottom, N2, we have 8.5 times 10 to the minus 1. And for H2, we have 3.1 times 10 to the minus 3, and then this value is going to be cubed. By the way, just as a quick note, to do this, the only reason we can solve for K by plugging these numbers in like this is because these values are equilibrium concentrations. If the problem said that these were initial concentrations, we would not be able to use the initial concentrations in here. So it has to be, when you're using your equilibrium expression, you need to be using equilibrium concentrations for that to work. So let's crunch our numbers here. Get my calculator. What I'm going to do is I'm going to do this kind of separately. So I'm going to get my value for the top, I'm going to get a value for the bottom, and then I'm going to divide them out just to make sure I don't make any mistakes. Because sometimes when you try to plug all these numbers in as one thing in your calculator, it's a good way to make a mistake if you're doing that. But I'm going to do this. Let's see, 3.1 times 10 to the negative 2. I'm going to square that first. So on the top we have 9.61 times 10 to the minus 4. And on the bottom we have 8.5 times 10 to the negative 1. We're going to multiply that by 3.1 times 10 to the third, but we're going to cube that value. So on the bottom we have 2.53 times 10 to the negative 8. And let's divide these values and see what we get. 9.61 times 10 to the negative 4 divided by 2.53 times 10 to the negative 8. And so I'm going to put this, let's see, I'm going to put this in scientific notation. 3.8 times 10 to the 1, 2, 3, 4, 5 times 10 to the 5th. 3.8 times 10 to the 5th. And that would be my K value now for this reaction. Now K values, you're going to notice, are going to be unitless numbers. So you're not going to have any, it's not going to be molarity or anything like that. K values are unitless, and so that would be my final answer for that one. Now, along with that, what does that K value, what does that tell us about the reaction? What is the significance of figuring out that K value? What K values tell us, they give us an idea of where a reaction is going to lie. So If you have a large K value, what that means is that reaction is product favored. It means that when it reaches equilibrium, you have a lot of products and not very much reactants. And that makes sense because to figure out a K value, all we have to do is take the products divided by the reactants. And so if you have a lot of products, well then this number is going to be really big, this number is going to be really small, which is why we end up with a large K value. If the K value is small, that means it's reactant favored. So the reverse is happening there. The number on the bottom is really big, the number on the top is really small, and so you get a small K value. It means it's reactant favored. The other ways we can say this is lies to the right or lies to the left. It's just another way of saying product or reactant favored. So if it lies to the right, again, that means you have a lot of products. If it lies to the left, it means you have a lot of reactants at equilibrium. If your K value is approximately 1 or close to it, it means you have relatively equal amounts of products and reactants at equilibrium. A couple of things to differentiate between equilibrium positions or equilibrium position. That refers to what are your concentrations basically, what are the concentrations of each thing once equilibrium is reached. So that can be many different possibilities. The only thing that your equilibrium positions depend on is what you initially start with in the reaction. So depending on what we initially start with here, we could start with maybe a lot of this, but if we allow it to reach equilibrium, it's going to reach a bunch of different concentrations depending on what you start with. The equilibrium constant though, so that's our K value, that's always going to be the same value for a reaction regardless of what the initial concentrations you start with. Because for every reaction, it's going to be a specific ratio of products to reactants that it wants to get to. It's always going to be the same ratio. Now, there is one thing that your K value does depend on, and that is the temperature. So K value is temperature dependent. So if I were to do this reaction at, let's say, a much higher temperature, well then the rate's going to change, and so the K value will be different. But at a specific temperature, the K value will always be constant for a specific reaction. We can look at an example of this using this reaction right here. So here's our expression for it. Let's say we do two different experiments where we vary the initial concentrations. In experiment 1, we start with 1 molar of each of these and none of this. So that's the initial concentrations. We put those together, we let the reaction reach equilibrium, and this is what we end up with right here. So notice some of the N2 and H2 has been used up, and we have NH3 has been produced. If we plug those into our equilibrium expression, we get this value here, 6.02 times 10 to the negative 2. If we were to do that again in a second experiment, but this time the initial concentrations, we start with nothing here and 1 molar of this, and we allow that to come to equilibrium, we get these values here. Notice that they're very different than the equilibrium concentrations that I have here, but it still gives me the same K value. So if I were to plug these in to my expression, I still get the same value, 6.02 times 10 to the negative 2. It's because it doesn't matter whatever initial concentrations I would start with here, it's always going to reach a point where the ratio between my products and reactants gives me this value essentially. So that's the difference between an equilibrium position, so these right here are showing you the positions of each thing, and then your equilibrium constant, basically where the reaction wants to get to is that K value.